Okay, so the Bohr's model of the atom, Niels Bohr, won a Nobel Prize for this, and he knew at the time that it wasn't quite right. He knew there was something more that was going on here he wasn't getting, but it explains so much stuff. So here's the nucleus right here. You got the protons and the neutrons. And then outside of it, you have these energy levels, principal energy levels, or shells. N equals 1, N equals 2, N equals 3, N equals 4, and so on and so forth. Okay, and what he said is that electrons are in their ground state, and wherever that is, it could be 1, 2, 3, or 4, but they're in a ground state, and they jump up because they absorb energy, and they jump up to higher levels. But when they jump, they have to jump to these discrete energy levels. And this is where quantum mechanics kind of took root, because this is a quantized amount of energy. So you absorb a certain amount of energy, say that much energy, you get nothing. You have to absorb this much energy and you get to level 2. Absorb this much, you get to level 3, this much 4. It's like putting in 4 quarters, say a dollar for a bottle of Gatorade. 4 quarters, you get a bottle of Gatorade. 3 quarters, you get nothing. 5 quarters, you get 1 bottle of Gatorade. So it's the same kind of thing. It's quantized. These are the available energy levels. Now, what goes up must come down, so it falls back down, and what he said is then this emits a photon of light. So we just got done talking about photons and wavelengths and frequencies and energies. Well, that is where this photon is coming from. It's these electrons jumping because they get excited, energy goes in, absorbed, like from a fire or from electricity or something. They get this energy, they jump up to these quantized levels, then they fall back down, and these chunks of energy, these photons, correspond to a wavelength, a frequency, an energy that we've calculated previously. All right, so what he said was that electrons are in their regular state, and this is called ground state. And we're going to, in the next video, start putting electrons in their ground state where they belong. But when they absorb energy and jump, they go to what's called an excited state. And they, again, do this in quantized little packets. Jumping, they absorb a photon of light, any light, electromagnetic radiation. It could be anything. It could be visible, it could be a gamma ray, whatever. Photon light, and falling, they emit a photon of light, and we can see that. All right, the farther they jump or fall, the greater the energy. Okay, so we calculate that energy from before. If we calculate the E for 5 to 2, we're going to get a bigger E than if we're going like from 3 to 2. Now, this different pattern of falling gives rise to a line spectrum, which is unique to every element. So every element has their electrons in a ground state. All these electrons do their jumping and their falling to certain discrete energy levels. And when they do that falling, they emit a line of red, maybe a line of green. Now what you're going to want to do in your book is to look up the line spectrum of hydrogen, which I believe is on page like 390 something. And you're going to see 3 or 4 different lines. I think there's a purple one, a green one, a blue one, and a red one, I believe. And those lines at their different wavelengths represent hydrogen. Now, white light would be continuous. This would be all the colors of the rainbow, a continuous spectrum, all the colors. When an element undergoes some excitement from, whatever, we were going to put them in the fire on lab day, or you plug them in, the neon lights you plug in, run a current through it, and the electrons get excited, they jump up, they fall down, and depending on the gas that's in the tube, the chemical that we put in the fire, that's going to be a unique line spectrum. So you should definitely look up hydrogen. All right, here is actually what you should see. I think you'll see a purple one too, but a purple, a blue, a green, and red. Notice the farther they're falling, in this case to 4 to 1, corresponds to blue, which is a greater energy than green, which is only following this distance from here to here, corresponding to green, which has less energy. Check that chart again. And then you have red just going from 2 to 1, and red doesn't have as much energy. But this is the line spectrum for hydrogen, and this is caused by these electrons falling in discrete packets of energy. So the one thing Bohr needed to do, though, is he knew that it needed to go further. And we have this idea that the electrons are orbiting the nucleus, but they are not. They don't orbit the nucleus. They reside in what's called wave functions. So these little rings that we're drawing around for Bohr's model of the atom, like so n equals 1, n equals 2, 3, 4, 5, way, way, way more complicated than that. Okay, so only these particular things are allowed. Remember, discrete quantized energy, and electrons reside. Now, what do electrons do? We really can't know. Electrons reside in energy levels around the nucleus called orbitals. They're not orbits, though. Orbitals are areas of high probability. So you can say with high certainty, yeah, 90% of the time, electron probably is going to be there. Where the probability of finding an electron is fairly high, never certain. This is called a wave function. It's a mathematically defined area of high probability. Crazy hard math. Look up de Broglie and Schrödinger, some of the forefathers of quantum physics. Schrödinger's cat. Heisenberg's uncertainty principle. You can never tell where an electron is for certain. The position and speed of an electron, and I don't have any room to finish this. The position and speed of an electron cannot be accurately known. Once you focus it on the position, you lose the speed. If you try to focus it on the speed, you lose, the position gets more and more nebulous. There are areas, though, of zero probability where we can say it absolutely never is, and those are called nodes. So one of the interesting things in quantum physics is the fact that these little rings that we draw in Bohr's model of the atom, these little things right here, are considered orbitals. These are the wave functions, areas of high probability where probably we're going to find the electron. These areas in between are called nodes, zero chance of ever finding them there. So then you think, well, here I've got an electron and they're supposed to be jumping and falling through these areas of zero probability. And they can't. They can never occur in between. So that's one of the mysteries of the quantum world. How do they get from one orbital to the next, but with never going through? And that's, again, one of the great mysteries of quantum mechanics. They call it a quantum leap. All right, so take a look on page 398. It shows us some maps. These are the mathematically defined areas of high probability. They look kind of weird. Look on, there's an S, it's on page 399. If you look at the top, there's a little yellow box. And there's a yellow or a pink sphere, okay? And this is, again, mathematically defined area of high probability. This is called an S. Then if you go this is for n equals 1. When you go to n equals 2, right above it, you see a larger sphere. Okay, again, there's this pink. And then you see 3 weird-looking dumbbell things. And those are called p orbitals. It's a p sublevel. And those are also areas of high probability. So here they are. Here's an S, some p's, and some d's. It's kind of good to just keep the basic shape. I usually call these dumbbells, call these clovers, call this a sphere. Okay, so this idea seems really strange, but we see the results all the time. Fireworks. Okay, here's some colors you should jot down. That's when you put those in. I think this was actually supposed to be in the next slide, but I'm going to keep going and we'll overlap a little bit. So what we have to do is try to find places for electrons. And when we do this, we have these labeled, like the Bohr's model of the atom, n equals 1, 2, 3, 4, and so on. Each energy level has that many sublevels. So energy level 1 has one sublevel. It's S, looks like a sphere. N equals 2, as 2. It has an S that looks like a sphere and a P which has 3 dumbbells. Okay, 3 orbitals, 3 dumbbells. This has 1 orbital, 1 sphere. Doesn't look like a ring, does it? In n equals 3, when we get to n equals 3, that has 3 sublevels. S, which has 1 orbital, it's a sphere. P, which has 3 orbitals, looking like dumbbells. And it also has a D, which is 5 orbitals, looks like little clovers. For energy level 4, when we get out here, we have an S, a sphere, a P, 3 dumbbells, D, 5 clovers, and if you've seen a pattern here, F, it has 7 orbitals. They look a little bit like elongated flowers or daisies. That all seems pretty weird. This is a kind of a synopsis. Remember, I put this in capitals because I don't care what you got going here. It could be a sphere. We got dumbbells going. We have clovers. Like I said, looks a little bit like daisies. I have no earthly idea what that looks like. Doesn't matter. 2 electrons per orbital. Pauli exclusion principle. They have opposite spins, 2 electrons per orbital. Doesn't matter what kind of there. So just as a recap, this is what we're looking at. N equals 1 only has an S, holds 2 electrons, 1 orbital. N equals 2 would have an S and a P. S could hold 2 in its 1 orbital. P could hold 6 in its 3 orbitals. N equals 3 would have an SPD. S could hold 2. P could hold 6. D could hold 10 because it's 5 orbitals for a total of 18 electrons. So in N equals 3, we could fit in 18 electrons if we needed to. If you look like something like platinum with 78 electrons, we're going to need a lot of room. N equals 4, you'd have S, P, D, and F. S could hold 2. P could hold 6. D could hold 10. F could hold 14 because of its 7 orbitals.